So one of the things that I love about MIT is, as we think about being at the cutting edge, is this idea of, rethinking our assumptions. And so sometimes that means like saying, okay, here's what was known in the past, but we have these new tools that we can use to kind of re-answer a new question or re-answer an old question. And so when I think about combining new technologies with old approaches, one of the examples that I love that we've done recently is we kind of had this very crazy idea about thinking about immune responses and viral escape. And so a really talented graduate student who's co-advised by myself and another faculty member here at MIT, we said, okay, well, if we think about, I often tell my friends or my family, like I come from a family of non-science practitioners, so a good analogy can go a very long way. And so, thinking about explaining viral escape to my grandma, I tell her, what is viral escape? Viral escape is kind of like taking a sentence, changing a single word in that sentence. The sentence is still grammatical, but this meaning has changed a lot. And so the example that we often use is you could think about the boy pats the dog as the original sentence, and then you can change one letter in that sentence to become the boy eats the dog. That's still grammatical, but it's very, very different as opposed to changing the boy pats the dog to the boy pets the dog. That's still a very similar sentence. So that's like a really interesting analogy, but what we said is we could actually formalize this. And so if we actually hop back into the semantics literature, there's this concept of the distributional theory of semantics, which the way to think about this is you shall know a word by the company it keeps. So you can really kind of understand and learn kind of language patterns by looking at how different words in a sentence co-occur. And so there are these really great new machine learning algorithms that basically do this at scale. So if you think about how Gmail is predicting the next word of your sentence, this is basically using this distributional theory of semantics. And so we said, okay, this works really great for English language, but could it be possible that these same model frameworks could be used for understanding viral evolution? And so in fact, what we did is we said, let's use the same kind of state-of-the-art computational approaches to ask a very age-old question about how do viruses escape the immune system. So what we did is we actually took all of the publicly available viral sequences that were out there for different viral proteins, coronavirus spike, influenza hemagglutinin, and we created what are called these language models, which are basically what's on the back end of Gmail's next word predictor. And what we said is, okay, if these language models could simultaneously predict protein grammar, but also identify those amino acid changes in the protein that we would categorize as high semantic change, what would that actually do? And so what we show is that actually when we combine prioritizing both grammar, and high semantic change, what the algorithm can in fact do is it can predict the amino acid mutations to a protein, to viral proteins that actually allow you to escape antibodies. So that to me is just kind of an amazing testament of leveraging this old concept from semantics, these state-of-the-art machine learning algorithms, and then applying them to an entirely different problem. We found a good analogy, and that analogy actually worked out incredibly well. In my group, we think about how are we going to get to a TB vaccine? Like, that is my goal. When I retire, I would like to be able to say, we brought forward some TB vaccines, grounded in the questions that we really think are essential to answer. And to me, those questions that I think that are essential to answer are, one, how do you actually leverage the immune system, or how does the immune system actually kill the bacterium? That is a central goal, right? And so, okay, so that's goal number one, is really trying to understand how this happens at a molecular level. But then we can understand how it works, but then we need to actually push the system to do that. And so then the second question we want to be able to answer is, how do you actually modulate the immune system to move it in a direction that would actually allow you to target infected cells and get them to do what you want? And so those are the two questions that we ask. And when I think about how do we go about the problem, I've been really fortunate to have a wide array of kind of training in the biological sciences and kind of the engineering sciences and also the computational sciences that, what I tell people when they join my group is that, I'm not married to a particular technology. I like to be of the mindset that whatever the best way to answer the question is the way that we proceed. But I think one of the things that also is coupled with that is that I want to be as exhaustive in our measurement as possible. If you only go in looking for one thing, you're only going to find one thing. But if you can really cast a wide net and have a systematic strategy for kind of parsing through all of the different measurements that you can make to characterize your biological system, then you have a better chance of understanding what's really going on. So we use a whole array of what would be called systems biology techniques, where we can characterize the immune response to TB infection at scale. But then you get a lot of data, and then you need to be able to actually understand what are the signals that matter. So we use a whole host of computational techniques and mathematical techniques to really kind of parse through and say, these things are going together, and whenever these two things go together, we see bacterial control.